Alright, this is section 11.2, chords and arcs. So what we're going to do today is learn about this little line right here. And this line right here is called a chord, and it's a segment whose endpoints are on a circle. So it's never going to extend out to either side. It's going to always stop and have a point that's on the circle right here and here. Now, we have a few theorems today, and you need to write them all down. It says Theorem 11.4, within a circle or in congruent circles, congruent central angles have congruent chords. So, for example, if I had lines that went like this, and this was an angle, and then let's say I duplicate this and I put it right here, that means that if these two angles are congruent, then these chords here are congruent. And then the next one says congruent chords have congruent arcs. So it's saying that if PQ is congruent in both of these circles, then our arcs, or our curved line going from P to Q, are also congruent. So our arcs are congruent. And then it says congruent arcs have congruent angles. And we kind of already know that. We know that if this arc is so many degrees, then this has to be congruent to this. Okay, so here's our first example. It says the two circles are congruent. What can you conclude? So first thing I noticed right off the bat is that I have vertical angles right here. So I know that these two angles are congruent to each other and these two angles are congruent to each other. So I can write angle TFE is congruent to angle HFG. So I can say that TFE, this angle here, is congruent to HFG. Now remember, the vertex of your angle has to be the center letter. So I have angle F in the center. And then I can also say, so this is one thing that I can say. The second thing that I can say is that angle JKN is congruent to angle MKL. Sorry. JKN is congruent to MKL. So I know that these two angles are congruent. Now I know lots of other things too. I know that if these angles are congruent, then the arcs are also congruent. So I can say, as my next thing, is arc ET, and remember we mark arc with a little arc over the top, is congruent to arc GH, which is also congruent to arc JN, which is also congruent to arc ML. So I'm saying that this arc is congruent to this arc, which is congruent to this arc, which is congruent to this arc. Now, I know that if my arcs are congruent, I know that my chord is congruent. So I can say the same thing about all of these little segments. So the fourth thing I can say is that ET, segment ET, is congruent to segment GH, which is also congruent to segment JN, which is also congruent to segment ML. Now, I knew all of these things because of these theorems that we wrote over here on this page. So, our next theorem, it says within a circle or in congruent circles, chords equidistant from the center are congruent. So, the distance, if this distance here is congruent to this distance, then my chords are congruent. And remember, my chords are a line that have endpoints on the circle. And then I also have congruent chords are equidistant from the center. So that means if this chord here is congruent to this chord, then the distance from the center to the chord, the distance from the center to the chord is the same. So if I look at this first example, I know that this side is 5, and if I take 2 plus 2.5 plus 2.5, I figure out that this side is also 5. So using number 2 of my theorem, it says that if these two chords are congruent, then the distance from my center is also congruent. So if this is 2, then x has to also equal 2. Now, all this stuff seems relatively simple, except for the fact that if you don't know these theorems. So the thing that you need to remember this section is to memorize your theorems and know the properties of your circles. So, this next one says that we have the distance from here to here is 3.5, and I know this part is congruent. So I know this is also 3.5. And then I have my double lines with this one being 5, so this side has to also be 5. And then I'm solving for this whole line. So my first part says chords equidistant from the center are congruent. So the distance is equal from the center to each of my chords. So that means this chord here is congruent to this chord here. And this whole chord is equal to 10. So x has to be equal to 10. Now, make sure when you're taking your notes, you're drawing these pictures. If you just write 2.5 plus 2.5 equals 5 and then x equals 2 on your notes, you're not going to have any idea what any of that means. All right, our last set of theorems. One of our theorems says, in a circle, a diameter is perpendicular to a chord bisects the chord and its arc. So what that's saying is if I have a circle, like so, it's saying that a diameter is perpendicular if the diameter is perpendicular to a chord. So here's my diameter, here's my chord, and if it's perpendicular, that means that the chord bisects, or the diameter bisects the chord and the arc. So that means that this distance is congruent to this one, and this arc is also congruent to this arc. So all it's saying is that if the diameter and the chord are perpendicular, then it cuts the chord in half. Now the next one says, in a circle, a diameter that bisects a chord is perpendicular to the chord. It's basically the exact same thing as this. It's saying if I know that these two pieces are congruent, then this has to be a right angle because it has to be perpendicular. And the last one says, in a circle, the perpendicular bisector of a chord contains the center of a circle. So it's saying if I have a perpendicular bisector of a chord, so basically my diameter, it has to go through the center of the circle, which makes sense. If it's cutting this line in half, then this diameter has to go directly through the center of my circle. Obviously, I'm not perfect at drawing with this airliner, but this is the general concept. So the first one says, solve for r. So since I know that this piece here is 90 degrees, and I could extend this and make this my diameter here, and then it could go this way too. Whoa. So if I have this, I can say that since this is perpendicular, or my chord is perpendicular to my diameter, that these two pieces are congruent. And if the whole thing is 14, then that means this little piece is 7. Now I have a right triangle, so I can solve for r. So I'm going to have 7 squared plus 3 squared is equal to r squared. 7 squared is 49, plus 3 squared is 9, equals r squared. So then I have 57 is equal to r squared. And we all know that we need to take the square root to get r by itself. So I have r is approximately 7.6. Now you could have left it as a simplified radical, and that's fine, but you can also change it to a decimal. So now the next one is about the same, but a little bit different. This time I know that these two pieces are the same. So if I were to extend my diameter through the center, and if this side is congruent to this side, then that means this has to be a right angle. So now I made a right triangle again. So we first figured out that BC is perpendicular to AC because of our theorem that we had up here. So now I can say, solving for y, I have y squared plus 11 squared equals 15 squared. So then I have y squared plus 121 is equal to 15 squared is 225. So minus 121 from both sides. So then I get y squared is equal to 104. And then I square root both sides. So y is going to be approximately 10.2. All right, that's all I got for you. I will see you tomorrow.